Today we're going to be talking about valid and invalid arguments. An argument is a sequence of statements, and an argument form is a sequence of statement forms. All statements in an argument and all statement forms in an argument form, except for the final one, are called the premises, or assumptions, or hypotheses. The final statement or statement form is called the conclusion. Let's see here. Just this symbol here. Remember, that means therefore. And it's normally placed just before the conclusion. To say that an argument form is valid means that no matter what particular statements are substituted for the statement variables in its premises, if the resulting premises are all true, then the conclusion is also true. To say that an argument is valid means that its form is valid. Testing an argument form for validity. Identify the premises and conclusion of the argument form. Then construct a truth table showing the truth values for all the premises and the conclusion. And then a row of the truth table in which all the premises are true is called a critical row. If there is a critical row in which the conclusion is false, then it is possible for an argument of the given form to have true premises and a false conclusion, and so the argument form is invalid. If the conclusion is in every critical row is true, then the argument form is valid. All right, let's do an example here. We'll do, let's see here. I'll clear that. If P, then Q or not R. Okay. If Q, then P and R. Therefore, P implies R. Is that a valid or a invalid argument? The truth table, a little bit big, but we'll go for it here. P, Q, and R. I'm gonna run out of room here. Well, I'll see if I can do it. All right. Now, the components of this argument we're going to evaluate as well. So not R is going to be false, true, false, true, false, true, false, true. Then you have Q or not R. So Q or not R. So that would be true, true, false, true, 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 false, and true. And we have P and R. P and R is true here, false, true, false, and then false all the way down because P is false. Now we can construct the truth tables for our premises. The first premise, premise 1, here, P implies Q or not R. That's going to be true. That's going to be true. That's going to be false. That's going to be true. And these are going to be true as well, because by default. Okay. So it's just that one false and the rest are true. The second premise is Q implies P and R. So Q implies P and R. That's going to be true. That's going to be true. No, that's going to be false. Sorry. Looking at the wrong column. False is going to be true by default. False is going to be true by default. True and false is going to be false. True and false is going to be false. And then these two are going to be true by default. Okay, now we have the two premises evaluated. Now you can identify the critical rows. The critical rows are where both premises are true. So that's going to be this row right here, this row right here, and this row, and this row. Now, what we need to know is the conclusion, is this true in those four rows? So we have P implies R. That's going to be true. That's going to be false. And that's going to be true by default, and that's going to be true by default. So what we have is a critical row where the premises are true and the conclusion is false. So this argument form is not valid. You understand? You get why that's true? Because the premises are true and the conclusion is false in one situation. It has to be true in all critical rows. See, these don't matter because they're not critical rows. But this one makes this argument invalid. So You can construct the truth tables and see where the truths and the falses lie, and determine the validity of an argument that way. It doesn't really matter what P and Q and R stand for. An argument constructed in this fashion is not going to be valid. We'll get more into fallacies and errors in logic later today. But an argument form that contains two premises and a conclusion is called a syllogism. The two premises are called the major premise and the minor premise. One form of syllogism that is well known is modus ponens. Which is Latin for something I don't remember. But it has the following form. If P then Q, P, therefore Q. If P then Q is true, and P is true, then Q must be true. So if you look at the truth table, no, that's false. P implies Q is going to be true, false, true, true. Now the critical rows are where P is true and P implies Q is true. That's only going to be this one row right here. So this one and this one. Now, is Q true in that row as well? Yes. Therefore, it is a valid argument form. Another famous syllogism, modus tollens. If P then Q, not Q, therefore not P. Again, you can look at the truth table here. I do P, Q, and let's see here. P implies Q. Not Q. And not P. Is false. true, true. So are the only row where this premise and this premise are both true is right here, and not P is true in that place. So this is a valid argument. Easily verified with the truth table. Now, example. A little example of this. If P is equal to, let's see here, and Q equals if there are more pigeons than there are pigeonholes, then at least 2 pigeons roost in the same hole. There are more pigeons than there are pigeonholes, therefore at least 2 pigeons roost in the same hole. So this has the form of P, then Q, P, therefore Q. Modus ponens. So it's a valid argument, showing that Q is true. That 2 pigeons are in fact in at least one hole. Additional argument forms, some rules of inference. First you have generalization. First of all, a rule of inference is a form of argument that is valid. Generalization. P is true, therefore P or Q is true. If P is true, and then it doesn't matter what you OR it with, the result is going to be true. So you can generalize that way. Specialization. P and Q. Therefore P. Or therefore Q. It can go either way. But if P and Q is true, then both P and Q are both true. Therefore, P is true. You can use this for discarding extraneous information, focusing instead on the property that you are interested in. Let's see here. Elimination. P or Q, not Q, therefore P. If P or Q is true, one of the two has to be true. But you're saying that Q is not true, so that must mean P is true. Let's see here, transitivity. If P is in Q, and if Q then R, therefore P implies R. Change of the if-then statements can be reduced to the first statement implying the last in this case. I skipped over this in the last class. But let's see here. Yeah, P implies the last. The first one implies the last one through transitivity. Division into cases. P or Q is true. If P, then R is true. Q implies R is true. Therefore, R is true. This is a little bit more involved, but what we have here is in a situation that P or Q is true. One of them has to be true. Okay. So one of these two has to be true other than truth by default. And if it's true by not being at default, then R must be true. Therefore, R is true. Because you've divided it into the different possibilities, divided into the different cases, and it often happens that when one thing or another is true, if you can show that in either case a certain conclusion follows, then this conclusion must also be true. All right, let's see here. Big example. You're about to leave for class in the morning and discover that you do not have your glasses. You know the following statements are true. If I was reading my class notes in the kitchen, then my glasses are on the kitchen table. If my glasses are on the kitchen table, then I saw them at breakfast. I did not see my glasses at breakfast. I was reading my class notes in the living room, or I was reading my class notes in the kitchen. If I was reading my class notes in the living room, then my glasses are on the coffee table. Where are the glasses? Now you can probably figure that out in your head pretty quickly, but let's look at it formally. Let's see here. RK. equals reading in kitchen. GK, glasses in kitchen. SB, saw glasses at breakfast. RL, reading in living room. GC, glasses on the coffee table. Okay. So you do the sequence of steps to reach an answer. Start off with what from the statement, original statement. If R and then K, if R at K, then GK. If you were reading in the kitchen, the glasses would be in the kitchen. If your glasses were in the kitchen, you would have saw them at breakfast. Therefore, if you were reading in the kitchen, you would have seen them at breakfast. That's by transitivity. If RK, then SB. If RK, then SB. From your previous conclusion here. Not SB. You did not see your glasses at breakfast. Therefore, you were not reading in the kitchen. Modus tollens. RL or RK. Either you were reading in the living room or you're reading in the kitchen. From the previous conclusion, you know that not RK. Therefore, reading in the living room by elimination. If RL, then GC. If you're reading in the living room, then your glasses are on the coffee table. From the previous one, you know that RL is true. Therefore, the glasses are on the coffee table by modus ponens. See how you go through the steps and logically conclude the answer to the underlying question. Like I said, probably some of you at least gathered where the glasses were from the opening statement, but what formally is going on in your head, mathematically formalized, is something like this. Like I said at the beginning of class, this is mathematically formulating common sense, mathematically formalizing it, and giving it a shorthand and that sort of thing. Now, there are some fallacies. A fallacy is an error in reasoning that results in an invalid argument. 3 common fallacies. Using ambiguous premises. You don't know whether or not your premise is true or not. It can go either way. Circular reasoning. And jumping to a conclusion. Skipping a step. Now you can show that an argument is invalid by constructing a truth table. If there is a critical row with that has a false conclusion, then the argument is invalid. Another way to find an argument of the same is to find an argument of the same for that with true premises and a false conclusion. Some other fallacies or errors in logic. Converse error. Comes from the converse of a conditional. If P then Q, Q, therefore P. It looks similar to modus ponens, but it's not. It is an invalid argument. Put it into words. A little example. If Zeke is a cheater, then Zeke sits in the back row. Zeke sits in the back row, therefore Zeke is a cheater. Doesn't quite work that way, does it? No. So that is an invalid form of argument. Inverse error is if P then Q, not P, therefore not Q. Looks like modus tollens, but it's not. It is invalid. An example of this would be if these two vertices are adjacent, then they do not have the same color. These two vertices are not adjacent, therefore these two vertices have the same color. Doesn't quite work that way. So, yeah, it's a invalid form. Then there's the argument with a false premise. If a premise of an argument is false, then the argument is invalid. Take the argument. If Canada is north of the United States, then temperatures in Canada never rise above freezing. Canada is north of the United States, therefore the temperatures in Canada never rise above freezing. Doesn't quite work that way because the first statement is false. It's a valid form, modus ponens, but it's not a sound argument because the first premise is false. So it throws the whole argument out the window. An argument is called sound if and only if it is valid and all its premises are true. An argument that is not sound is called unsound. We got contradictions and valid arguments. If you can show that the supposition that statement P is false leads logically to a conclusion or logically to a contradiction, then you can conclude that P is true. So, show the following argument form is valid here. If P, then contradiction. I'm sorry. If not P. Not P is a contradiction. Therefore, P. So, do the truth table for that. True, false, false, true. Contradictions are always false. Not P implies a contradiction. That's true by default. And that's false. So if you look at the premise, this is the only critical row, and in it, the conclusion is also true. Therefore, it is a valid form of argument. Let's see here. Went through that pretty quick. I stopped here in the last session. The next section is the application, an application section talking about digital logic circuits, which I think is inappropriate for this class. I think it should be reserved for digital logic class, but I didn't write the book. So we'll take care of that on Tuesday. That'll wrap up chapter 2. And then Thursday we will have the test on chapter 2 and 1. It'll be cumulative. So next Thursday, have a test. In the meantime, have a good weekend. See you on Tuesday. We'll wrap up chapter 2. Have a good day.